if I'm lucky, I'll get an office in Ronald Reagan Building. But right now, of course, it's all work from home.
Yeah.
Unless you happen to be in DC, in which case they'll assign you an office space. But it is pretty clear that they don't really want us to come because it increases the risk factor.
Absolutely.
Yeah. So it kind of. All right. How are we doing on time? It's about time, right?
Yeah, it is.
Okay. Let's then get going. We have quite a few people, and people will be coming in. Alex is here from Illinois. My colleague Octo is here. Tad is here from Brock. Savi is here from Geneseo. Good to see you. Great. Okay, let's get going. I will introduce Chris. It's really fantastic to have Chris. I mean, it's been what, 25 years or so since I had you in Buffalo. So our speaker today is Professor Chris Sorensen from the physics department at Kansas State University. The title of the talk is Of Soot and Sunflowers. Excuse my throat, I don't know what's happening. So Chris Sorensen is currently the Cortelyou Rust University Distinguished Professor and a University Distinguished Teaching Scholar in the departments of physics and chemistry at Kansas State University. He received a PhD in physics from the University of Colorado in 1977, and in 2008 was named a Norlin Distinguished Alumnus. He's a condensed matter experimentalist, and through the years, he has studied many topics, such as water in aqueous solutions, nanoparticle synthesis, aggregation and gelation of particulate systems, and particulate light scattering. Chris is a fellow of the American Physical Society, the American Association for the Advancement of Science, and the American Association for Aerosol Research. In 2007, he was named the Case Carnegie Foundation United States Professor of the Year for doctoral universities. This is an extremely high honor. I checked it out. So congratulations, Chris, for that. And with that, let's get going.
Okay, thank you, Surajit. And truly, it's an honor to be invited to this distinguished lecture series. Looking at the other names and the accomplishments of previous speakers, I hope I at least fit within a standard deviation of their high marks.
Oh, goodness.
So yeah, today I'm going to talk about soot and sunflowers. I'm going to find a connection through all the researches I've been doing. Some of this research dates back about 25 years when I last visited Surajit in Buffalo. I have here a picture. Many people don't know where Manhattan, Kansas is. People always think of Kansas as very flat. We live in the Flint Hills of Kansas, and here's a picture of one of those hills. This is also a picture of the tall grass prairie, and actually this is the so-called Kanza Prairie. That's a bunch of hiking trails as well as a research area for our field biologists. Well, okay, let's get going. Certainly I want to give you a talk outline here. Pretty much standard stuff there, all right? But let's get down to what the title first tells us about, and that's soot. So there I am. I've just stuck my finger in the tailpipe of my car. I've scraped out some black soot stuff, and this is the topic that's infatuated me for at least 25 or 30 years. And it's sort of ironic when you think about it. I have colleagues who are cosmologists, and they deal with the grand scale of the universe and how it all began. I have colleagues who are particle physicists, and they're worried about Higgs bosons and the origins of mass. And, you know, again, atomic physics colleagues who understand quantum mechanics to great detail. And here I am screwing around with a bunch of soot on the end of my finger. I mean, who could think of something less important? But I take advice from the great poet William Blake, and that's to see a world in a grain of sand and heaven in a wildflower, to hold infinity in the palm of your hand and eternity in an hour. And my grain of sand is that soot on the end of my finger. So I'm going to stick my finger with that soot in an electron microscope, and here's what I get. And it gets a little bit more interesting than just black smudgy soot. Let's see, I'm going to turn on my pointer here. Here we go, so I can point around a little bit. Yeah, it's kind of a lacy network of particles. These are carbon particles, as you might imagine. And it does have certainly a degree of attractiveness to it. So we might wonder how this lacy network came about. So we then move on to, for instance, the flame itself. On the left, I've got a luminous candle flame. And luminosity is because there's little solid soot particles in there. These here on the right-hand side that you can collect. And the way we collected this is we stick a cold knife blade into that flame. Thermal phoresis drives the hot soot particles onto the blade. And then, of course, we can stick it in an electron microscope and find these aggregates of soot. And let's remember, they're in the flame too. And another thing I do is I shine laser beams through flames like this, collect the scattered light, and then do in situ measurements on the soot as well. But you look at the particles over here and you wish you had a way of describing them. And even more so, as scientists, we wish we had a way of quantifying their structure. And indeed, that's the question that I'm going to address. So let's keep going. Here is a really important slide. Here again, I have another flame coming out of a simple Bunsen burner. And if I collect the soot early in the burner, I get this ensemble of soot aggregates. If I go higher in the burner, where the aggregates have had more time to grow in size, I get this. And I want to point out the scale bars, 300 microns and 1 micron. Essentially, we got 2.5 orders of magnitude different scale here, and I hope you'll agree that regardless of the different scale, we have similar morphologies. The shapes and morphologies don't seem to change, and we're going to call that scale invariance, invariant upon a scale change. Well, scale invariance, as Mandelbrot taught us, is ubiquitous in nature. The twigs of a tree look a heck of a lot like the tree itself. Lightning bolts have big wiggles and little wigglers yet. Here's a series of leaves on a fern, right? Scale invariance. The coastlines of various continents or lakes. Richardson, a seminal person long before our time, pointed out the scale invariance of coastlines, for instance. And of course, river tributaries, each are broccoli. Here's a little bit different. You know, all the others were random. This has a systematic nature to it. This is the logarithmic spiral of a nautilus, and it is scale invariant too, because as you go around, you go 1, 2, 4, 16. It's a logarithmic spiral, so it's scale invariant too. So scale invariance is out there in nature, and to summarize what Mandelbrot taught us, many human objects are not scale invariant, they're geometric, whereas nature seems to abound in these scale invariant objects, and Mandelbrot coined the term fractal. So now we're going to say that that anything with scale invariance, like my soot particles in the previous slide, they are then fractal aggregates. Now this idea first came about in 1979 with Forrest and Witten, who actually looked at soot. You can see a picture similar to one of the pictures I showed earlier. And they realized that there was a fractal nature to this. And along with the fractal nature, there's a scaling dimension, the so-called fractal dimension, which is a non-integer dimension that will describe how the scale changes how the mass of the objects change as we change the scale. So let's take a look at that. First of all, I got to define some things. So I'm going to have fractal aggregates like this. I'm going to give a scaling dimension. I'm going to use capital D for the most part for my scaling dimension. It's going to be less than the spatial dimension. I'll use little d for the spatial dimension. So there we've got 2 dimensions. I like to write the fundamental scaling relationship for a fractal aggregate is as follows. So we'll actually count the number of monomers in the aggregate. Each one of these little balls is a monomer, and you can kind of see that structure in the real picture. There'll be a prefactor. The important scaling relationship is that there'll be a size of the aggregate, which will be a radius of gyration. Essentially, that's a root mean squared radius. And then the number of monomers per aggregate scales as the size to the d power, the fractal dimension power, as so. So let's take a look at that. This is that slide I showed you earlier with the two different scales, 1 and 300 microns. And we can essentially measure this area of these things and relate it to the number of monomers in an aggregate. And we do that. We also then measure the radius of gyration of these aggregates, and we plot the number of monomers in the aggregate versus the radius of gyration. It's a double log plot. This data, these particles are clear down here at small sizes. These particles clear up here another 3.5 orders, 2.5 orders magnitude higher. But notice a remarkable trend. They all lie on the same line. That's really surprising. I think any physicist knows if you get 8 orders of magnitude of the same trend, you're doing pretty well. And it's all on a slope of 1.8 to tell us that the scaling of the number of monomers in an aggregate versus the aggregate size has a fractal dimension, a scaling dimension of 1.8. So now we've got a way of quantifying these aggregates. We claim we have a name, they're fractal aggregates, and we got a quantity. They have a scaling dimension, a fractal dimension of 1.8. Now, this turns out to be universal. So you can make aggregates and colloids. So here's some very early work back in the 80s after Forrest and Witten from the Waits group. These are gold nanoparticles that were in a colloid, destabilized, and they made this aggregate, and it has a fractal dimension of about 175. Here's some of our soot, fractal dimensions of 1.8. And within experimental error, these numbers are essentially the same. So we've got universality. Any type of material, if it aggregates via diffusion limited cluster aggregation, will yield a fractal of 1.8. Now I want to show that. I want to say the word again, diffusion limited cluster aggregation. What that essentially is, let me get this thing going. I have to end show. Oops, and then I have to hit the start button. And now I'm going to wonder if it's going to work for me or not. And it's not.
Press the no, I think.
Say what?
Here, do you need to press the yes or the no? We need to upgrade media objects. You don't want to upgrade anything, I don't think.
Yeah, well.
Well, it worked a little while ago.
I know. So I'll talk while this thing is trying to fix itself.
Mm-hmm.
So essentially, the idea is that, let's see. The idea is that the little particles diffuse by Brownian motion. And let's try this one more time.
Should work now. Just say no. It worked a while ago.
Yeah. So we dry run this and it worked. So we're going to have to go through this. The little monomeric particles diffuse by Brownian motion. When they bump into each other, since they're solid particles, they don't coalesce. Instead, they stick together. and they stick forever, and the resulting dimer becomes a cluster or an aggregate, and it continues to move by diffusion limited, by diffusion, Brownian diffusion. And if it then encounters yet another cluster, the clusters continue to grow. So we'll restart, and we won't try this yet again. Okay, this is the black hole of Kansas right here. All right. Well, actually, I want this slide. The slide that aborted on me yielded this result. So we start off with a bunch of monomers. Over here, we end up with a bunch of aggregates. We analyze the aggregates. Again, number of monomers versus radius of gyration. Log, we get a linear functionality, and we get, hence, this scaling relationship. This slope is typically on the order of 1.8 plus or minus a tenth via diffusion limited cluster aggregation. You might say that's an explanation. We do have an explanation. It's not really a theory. Let's remember, this is a computer experiment. So a lot of the work I do involves light scattering. That allows us to go into a flame or an aerosol or a colloid, and not actually sample the material, but do in situ measurements. This is one of our most recent devices, which I take great pride in. We can scatter light from 3/10 of a degree, clear out to 149. Actually, we're out to 160 degrees now, with a couple different devices. The aerosol would be coming straight out of the page here of the slide. That could be a flame, for instance, shining a laser in, collecting the scattered light, and getting what I call optical structure factor measurements. Here's an example from a methane flame. We're at different heights above the burner. As we go higher above the burner, the aggregates have more time to grow. Here's Q, an important variable. Q is related to the scattering angle, so we can change Q with the scattering angle. This is the scattering wave vector. It has units of inverse length. So you can see as we go to smaller Q, we're going to bigger sizes, and the intensity is proportional to the number of monomers in an aggregate. So it's kind of like we got number of monomers versus inverse size, and a linear relationship would have a slope of 1.75, which it does. So you can see the in situ measurement also yields fractal nature with a fractal dimension on the order of 1.8. That was a hot flame. They can be cold aerosols. Here's yet another example of the sorts of things we can do. All right. Well, so we were doing that sort of thing with some regularity and some success years ago. And I might back up and point out that ultimately, as you get to small enough Q, which is small enough angle, the intensity will round off and not increase anymore. And it's a simple diffraction type of situation. Matter of fact, this rounding off point tells us the size of the aggregates. Well, I had a student doing acetylene flames, and he came in and he says, you know, I keep going to smaller angles and I can't get the intensity to round off. And so I walked down to the lab, and we were in the dark lab. We got this bright, luminous yellow flame, the laser's on. It's really beautiful in there with all kinds of colors all over the place. And the flame just looked different. And so I leaned in real close, and I actually had to hold my finger in front of my nose because the flame was so doggone hot. And I looked in the flame, and it was all grainy. And I said, what the blank are we blanking scattering light for? I can see the blanking soot. So we got a very fast camera, and actually it wasn't a camera, it was a pulse laser. Let's see, this is another video. Cross your fingers for me. And this is what we saw. This is with a pulsed YAG laser, 9 nanoseconds. Look at that. So that's about a 1 millimeter wide flame. And you can see the soot. And they look like fractal aggregates, don't they? Yeah.
They do.
So we probed this further, and here's what we got. So this is a picture. This is a column of soot coming out of a Bunsen burner flame. I mean, this is not esoteric. This is not Atlas at CERN, all right? This is a Bunsen burner. And we had acetylene, a heavily sooting fuel. And as we increase the acetylene flow rate, we go from soot that you can't resolve with simple optical means to little grains of soot till finally, look at that. That's a continuous network of soot across the extent of the flame. We have gelled soot in a flame, which has, of course, all kinds of marvelous ramifications. Apparently these things here, let's go back to my pointer. Where's my pointer? Yeah. These things here are frozen margaritas, which sounds like that are gelled too. So that sounds like a lot of fun. So that gave me a new research direction, which was to study gelation. Here we go. Actually, I'm going to back up. I'm going to ask you a question. Let's go up in the atmosphere. Let's go inside of a cloud of water droplets. Let's suppose it hasn't started to rain yet, and the droplets are 1 micron in diameter on average, and the average separation is 10 microns, right? Fine. So with time, the droplets diffuse around, they hit each other, they stick. But remember, they're liquid, so they coalesce to form another spherical droplet, just bigger. Eventually, you get to have 1 millimeter sized droplets. Are they still 10 microns apart? Well, of course not, right? The question is, if it was a 10-to-1 ratio when it started, and now that you've grown to 1 millimeter, what's the average separation? And the answer is 10 millimeters. The ratio of size to separation stays the same. And the reason why is you're in a 3-dimensional space and you have 3-dimensional objects. Spheres are 3-dimensional objects. They have a scaling dimension of 3. Not so for fractals. So I'm going to define a nearest neighbor separation. There it is. I'm going to have my size of the aggregate, radius of gyration. I'm going to plot either one of these versus time. Aggregation's ensuing to the right. This is the number of monomers which per aggregate, which grows with time. And the nearest neighbor separation will follow this law. This is the log-log plot. So I've got slopes equal to the exponents. 1 over the spatial dimension is 1/3. On the other hand, the radius of gyration is proportional to the number of monomers to the 1 over the fractal dimension. And the fractal dimension is 1.8. In the inverse of 1.8, it's 0.55. And that's a bigger number than 1/3. And so the radius of gyration grows faster than the nearest neighbor separation. And ultimately, they're equal. And then they bump into each other, and that's the gel point. Notice there's some regimes, too, that popped up that we weren't expecting. There's a cluster dilute regime where they're really far apart compared to their size. But when they kind of start getting close, today we would say when they break the laws of social distancing, right? We'll call that cluster dense. And then, like I say, when they finally bump into each other, we'll call that the gel point. Now, we've added ideal gel point to do simple algebraic theory. We assume that they're all the same size, and they're all round, not oblong in some manner, so we can calculate this point. But our ideal gel point theory, which I won't elaborate on, turns out to work pretty well. So there are, in fact, aggregation regimes. There's cluster dilute, where the separation is much greater than the size. That's normal, DLCA kinetics, fractal dimensions of 1.8, and a kinetic exponent. I'll remind you, I had the number of monomers going as time to the z power, a kinetic exponent of 1. Now that's what everybody had been doing. There, like I said, there was fractal revolution in the 80s where everybody did all kinds of simulations with the computer and studied this, what I would now call cluster dilute aggregation kinetics. So we went into other regimes. So I used purple, that's the K-state color. We studied the cluster dense regime, found enhanced kinetics. So this kinetic exponent is greater than 1. A very fundamental equation that describes aggregation still works. This is a mean field theory. At the ideal gel point, the mean field theory fails, and what we will call superaggregates form. I will show you that. And then finally, there'll be a volume spanning single cluster. So let's explore these last 3 regimes now in some detail. So here's a fairly recent experiment. This is a colloid. We've got 40 nanometer polystyrene latex spheres. They're in water. And importantly, the volume fraction is rather small, 1 part in 10 to the 4th. They're DLVO potential stabilized, and we can destabilize the colloid by adding a little bit of an ionic salt. So we screen the coulombic repulsion. Then, sure enough, a diffusion limited cluster aggregation ensues. How do we know? Well, over here we have static light scattering measurements. Here's the intensity versus Q. And you can see that the overall trend here has the slope of 178. That's your DLCA fractal dimension. Notice the time's marching along. Student has to be very patient. This thing, 6,000 minutes, right? The other thing that's happening with time is this turnoff point keeps moving to smaller Q. And let's remember, smaller Q means bigger sizes because Q has inverse length. So the thing is growing all the time. The aggregates are growing, but they always have the same fractal dimension. We also did dynamic light scattering, where you measure a correlation function of the scattered light, correlation with time. And here again, you can see the correlation time is getting longer as we as the aggregation ensues, and there's some other details too. But from this, we can measure a radius of gyration, and from the dynamic light scattering, we can measure a hydrodynamic radius because it depends upon how fast the aggregates diffuse. And here are the results. So for both measurements of radii, there is indeed, early in the aggregation, a linear regime, a power law regime that has a slope of 1. The kinetic exponent is 1 as expected in the cluster dilute regime. But we cross over, there's a cluster dense regime. Now the growth is faster, implying that that kinetic exponent is bigger. And there's a number of simulations that we did too that I'm not showing you today. Everything fits well together with the simulations. Finally, after quite a while, the thing stops growing for the most part. And this is the gel regime. And we calculate what we call RGG. This is the radius of gyration at the gel point under the assumption of the ideal gel point theory. So we can calculate that, and it agrees fairly well with where this thing started to round off. So we feel we have a fairly consistent picture of gelation described by kinetics. Now, if you're not a gel guy or gal, that didn't mean a lot to you, but there really are 3 pictures of how gels form. Lots of people like to use percolation clusters to describe gelation. Lots of people like to use thermodynamics, and some people like us like to use kinetics. We think now our work has shown that the other 2 pale in productivity compared to our kinetic theory. Gelation is a kinetic work. Let me show you more about that. Here's an example of some recent simulations in collaboration with Chakrabarty at Washington University in St. Louis. We have a high volume fraction situation. Here's time, and here's log of the number of monomers. So this is a very rapid, right? Here's 10 monomers, and here's 1,000,000 monomers per cluster. And it pretty much comes up, it seems to bifurcate just a little bit. And those are two phases. Here's the sol phase in equilibrium with the gel phase. It's more evident at lower volume fractions. You can see here's the sol phase again, roughly 1,000 monomers per aggregate. But there's this gel phase up here at 1,000,000 monomers per aggregate. So although this gap is small on the graph, let's remember that's a factor of 1,000 times bigger. So there's the gel phase up there coming out of a strictly kinetic description. No need for thermodynamics to explain the two phases. Let's keep going. With our simple theory, we can predict when a gel will form. There's a kinetic coefficient that's related to the thermal energy kT, the viscosity of the surrounding fluid, things like that. Here's where the diffusion comes in. The other parameters here are the monomer size to the cube power and the volume fraction to the 2.5 power. These are both very strong functionalities. I graph it over here for aerosols. It would be different in a liquid because the viscosities would be different. And most aerosols, even the COVID aerosols that we heard about these days, have volume fractions no bigger than 10 to the minus 6, and typically smaller. And you can see, no matter what the size of the monomers might be, and these are very small monomers, right? We're down to atomic molecular dimensions here. The gel time for an aerosol is very long, 1,000 seconds or more. And indeed, nobody has ever seen an aerosol turn into a gel except that flame experiment of ours back in '98 with this acetylene, all right? But it does suggest that if we could make nanoparticles, and indeed the soot particles are, the monomers of soot are like 20 nanometers in diameter, that would be a radius of 10. And if we could make a very high volume fraction, we could get the gel time down into experimentally doable things. Up here, you don't have the time because the aerosol falls to the floor, right? Gravity pulls it down. They're not suspended up like you can in a colloid. So the question becomes, how can we create an aerosol of nanoparticles at this volume fraction? Well, we can. One can do simple math and say to yourself, if I have a mole of acetylene, at STP, I've got 2 moles of carbon, and I would have those 2 moles of carbon in a 22.4 liter chamber, and that would be 24 grams in there, and if they were 10 nanometers in size, I'd have a volume fraction of 10 to the minus 4 or so, and I should be able to gel it. So we actually did that. So you might notice some familiar names here if you know history. Here are 2 chambers that we filled with acetylene and oxygen. We used too much acetylene, you might say. We want carbon. We don't want carbon dioxide and water. So they were fuel rich. I might add the student who did these experiments, Corey Gerbing, was a graduate from the United States Military Academy at West Point. He was still in the Army. He was a captain in the cavalry. He drove tanks for a living. And so he absolutely loved this project because he got to blow shit up, all right? So you can see a simple spark plug up here. So the science is pretty easy. Thick walls, of course. So we filled these chambers with acetylene and oxygen, fuel rich. We detonated it, and we got the following. We gelled an aerosol. This is the stuff we made. When we first opened the chamber, we would wait like 10 minutes or so for the gelation to occur. Matter of fact, had we opened the chamber 10 seconds after the detonation, a big black cloud of smoke would have come out. So we left it alone for 10 minutes. And when we looked in, we had the darkest, blackest angel food cake you'd ever seen in your life. So we scooped that stuff out, and there it is. You can see it's centimeters in size. We call it an aerosol gel, and it's roughly 2.5 milligrams per cubic centimeter in density. I'll remind you the density of air is 1.3 milligrams per cubic centimeter at STP. So we made this stuff. Notice I call it an aerosol gel. A lot of you probably know that there are aerogels. And that's the result of gelation of particles in a liquid phase. So to distinguish what we made, I like to call these things aerosol gels. Matter of fact, we even got a patent on the process. The other thing that's really remarkable about this stuff is it is really black. I want to show you a close-up of how black it is. Now that's black, right? Okay, all joking aside. So what I have here is a cylinder. It's about, the window is probably 2 inches in diameter. The cylinder in length in and out of the plane of the view graph here is about 4 inches long. It is filled with acetylene and oxygen. And it's fuel rich, so we're going to make carbon. And I'm going to hit the button, and after a few seconds, you'll see a flash of light. That's the explosion that occurs. And then we'll see what happens after that. So here we go. Boom! Now, again, we made smoke. If we open it right away, smoke comes out, a big black cloud of smoke, but we left it alone for a few minutes. See it? There you go. Gelled soot. A cloud of smoke that turned into a gel. I think we're the only people who've ever done this. I've never seen anybody gel a cloud of smoke.
How deep is this?
It's about 4 inches deep. So you can see the person's hand. Yeah. So it's about 2 inches wide. And of course, we put the symbol of the K-State Wildcats in the background there just for, for advertisement purpose. All right, let me go back to full screen, I hope. Let's see, down here. There we go. Well, yeah, so we did this with silicon too. That was a lot of fun because we used silane, SiH4, the big brother of methane. Silane is pyrophoric. As soon as it sees air, it burns. And instead of making carbon dioxide, it makes silicon dioxide. Growing up in Nebraska and living in Kansas, I hear rumors that there are places thousands of miles away that have silicon dioxide next to the water. They call them beaches, but what would I know? Well, there's more. We also, like I said, scatter light, and it was in through that era that I improved my equipment from just simply scattering out in this Q range to adding small angle scattering to let us go to smaller Q. And when we had an acetylene air flame, much like I showed you that got this whole thing going, we found that that we would get these structure factors of intensity versus Q that actually had two regimes, two power law regimes. The standard 1.8, which we'd seen many times in flames, but then at small Q, large length scales, we got a 2.6. We collected the soot from these things too and found with electron microscopy 1.8 and 2.6 type fractals as well. Notice I've got an inverse Q here to show you some sizes. So submicron, it's 1.8, but supramicron, 10 microns for instance, it's 2.6. And what the light scattering implies is we now have a hybrid structure. So we get 1.8 for small scales, that's large Q. But at large scales, the overall structure has a fractal dimension of 2.6. So it's a hybrid. We collected the soot from other situations too. Here's an aggregate, and here's a 50 micron bars. This is really a big aggregate, and it's pretty much the result of gelation. And if we Fourier transform this aggregate, that's essentially the same as optical diffraction, so it's kind of analogous to light scattering. We get a lot of ripples and stuff, but the envelope has a slope of 2.5. That's the fractal dimension of this big guy here. If we zoom in on this big guy and capture this, just like Forrest and Witten did in 1979, and if we Fourier transform that, tell you what, let me go back to my pointer. If we Fourier transform that, we again get a bunch of ripples, of course, but we get an envelope of 1.8. So we've got this hybrid structure, classic DLCA aggregates that have come together to form a 2.5 fractal dimension superaggregate. And we did simulations and got the same thing. And here's our picture. So I coined the word superaggregate to imply not really big, but this hybrid structure. So we got little 1.8s that have come together and bounced into each other in the cluster dense regime. Remember that? When the separation to size ratio is essentially going to 1. And over a large scale, we get this 2.5 or 2.6. Well, more simulations, rather recent, 2017. I alluded to the fact that gelation is often viewed as a percolation phenomenon, but we like to contend that it's kinetic. So what we did is we did a DLCA simulation. This is simulation work. And we started with different volume fractions of monomers, and we plot the number of monomers divided by versus the radius of gyration, double log. And if we have a very small volume fraction, we get these black dots, and they all lie along the line of 1.8, as has been happening now for 30 or 40 years since the beginning of the fractal revolution. I might add the prefactor is important too, often ignored, but indeed important, as we have shown. The prefactor is also standard diffusion limited cluster aggregation particles. But notice some of these higher volume fractions start that way, and then they cross over to a slope of 2.5. There's your superaggregate forming. We've also then just did static percolation and plotted the percolation cluster with the open circles. There they are with a slope of 2.5, which many of you might be remembering now. That's the fractal dimension of a percolation cluster. And as it turns out, the coefficient is 0.6. So there seems to be a trend that the higher the initial volume fraction, the more it's going to look like percolation. Now, here we've normalized the radius of gyration by the monomer. But let's remember the picture of a superaggregate, right? The monomers now aren't important. The monomers of a superaggregate are the DLCA aggregates. You see, we have to rescale on that. This now becomes the monomer. So that's what I'm doing here. I reproduce that picture. We define an R naught as the radius of one of these aggregate monomers. We normalize that way, and all these data fall on the same curve with a slope of 2.5 and a prefactor of 0.6. And we conclude that kinetic diffusion limit aggregation leads to aggregates that are isomorphic with static percolation. Gelation is a kinetic process. It leads to percolated clusters in the long run, but it's definitely kinetic. Another thing I'll throw in is I was at a party one time. I rarely get invited to parties, but sometimes people invite me, and they had these tiki lamps copiously making soot. You look at these things, these pictures aren't what I quite wanted. But when I was at that party, I noticed the soot coming out of the tiki lamps some of it was as big as cornflakes. That's a gelation phenomenon. So if you're ever, physicists, we never get invited to parties. But if you get a chance, just keep your eyes open for that. All right, well, I've got about 15 more minutes here. Let's just do a little more. Surprises in the lab too. When we looked at our detonation, when we looked at our aerosol gels of carbon under electron microscope, we were expecting soot, little round balls of amorphous carbon, and we got little flakes, and as it turned out, the flakes were graphene. And that was back in 2013. We filed a patent, and now I've got a big program on making, we've scaled this up, and we're trying to sell it, and we're looking for venture capital. If any of you want to invest some money, please do. It has taken me off in a tangent. I've learned how to interact with business people and all kinds of neat stuff like this. So not quite as diverse as being a Jefferson Fellow, but still a lot of fun in my old age. And the fact that we discovered a very simple, economical, green way to make graphene has really proven to be important. But I'm not going to go there. That's another story. I want to finish with something that I think is really neat and that just frustrates the heck out of me because I think I'm not smart enough quite to really see what I'm doing here. But it's a simple theory, an analytical theory for the fractal dimension for DLCA aggregates, not only a fractal dimension, but the prefactor too, which today I haven't emphasized very much. And it's simple. So I go to the Yi Jing and I quote, by means of the easy and simple, we grasp the laws of the whole world. So here's my model. I'm going to start with two monomers. I'm going to stay in two dimensions. So I've got circular monomers, and I'm going to bring them together in a hierarchical fashion. 2, 4, 8, 16 monomers per cluster. So here's a dimer. There's n equals 2. And then I'm going to take another dimer and put it on the end of this. So we've got a side and we've got an end. And I get this. So that's end to end. If I did it yet again, I would have another set of 4 here. And if I keep this up forever, I'm going to get a fractal dimension of 1. It's going to be linear. Scaling dimension of 1. Notice I got a little f here now. Still fractal dimension. All right, let's do it again, but now let's do side-to-side aggregation. So again, I start off with 2 monomers. I form a dimer. I form a quadrimer. But now notice in the quadrimer, here's the side. I brought the other dimer up, and they hit side to side. And if I continue to do that, I'm going to get a big, flat network of circles stuck together. I'm going to get a scaling dimension 2. So now I'm going to do the cross situation. I'm going to do side-to-end aggregation. There's my dimer. And now here's another dimer, but I'm going to rotate this guy so that its end sticks to that side. All right? There you go. Got me? I'm even going to force this simple thing to stick linear like that. I'm not going to nestle in here or anything like that. So this is a very restricted model, all right? But now you can see I have an end and a side, and I'm going to continue to do this side-to-end aggregation, and I'm going to get something that looks like this. So there's the first 3 steps that we've seen, and you can see I do this now. Notice I always line things up and make nice rectangles. How realistic could this be? Then if you look at this carefully, listen to the numbers. This is 1 by 1, 2, 3, 5, 8, 13. It's the Fibonacci series, isn't it? Son of a gun. Yeah, I got the Fibonacci series. All right. And the ratio of consecutive Fibonacci numbers in the limit is the so-called divine proportion, or the golden mean. It's got a number, but it's certainly, you know, a grand number from the ancients, and it turns out to be 1.618, et cetera, et cetera. Turns out it's the most irrational number we know, if you know about continued fractions. Well, okay, but what's going on here? Let's keep track of what's going on here. Every time I made another step, I increased the mass by 2, right? 2, 4, 8, 16. Every time I did a step, I increased the dimensions by the golden mean, the divine proportion. So there's a scaling there, right? With each step, n increased by 2, the length increased by 5. So there's a fractal dimension. 2 equals the mass is proportional to the linear dimension, to the fractal dimension power, and you solve for that with the divine proportion, and you get 1.44. And indeed, that's what people get for simulations in 2 dimensions. Some people even float stuff on surfaces of liquids and watch aggregates form, and they get that number too. It works. Can we extend this to 3 dimensions? Yes, we can. Now, I could draw you a bunch of spheres and so on. I'm not going to do that. Instead, I'm just going to jump, and I'm going to define a 3-dimensional Fibonacci series. And now I'm going to start with 3 ones. And instead of nearest neighbors, I'm going to add second nearest neighbors. So for instance, 4 plus 9 is 13. 6 plus 13 is 19. All right? Then I can define a 3-dimensional divine proportion as the ratio of consecutive 3-dimensional Fibonacci numbers. And it's about 1.466, 465, whatever. Okay? Well, again, then there ought to be, if I make aggregates this way, every time the aggregate increases by a factor of 2 in the mass, but it increases in dimensions by this new divine proportion. Then log of 2 divided by log of this new divine proportion is 1.815, which is pretty damn close to correct too. So, like any good mathematician, which I am not, I go to n dimensions, right? I can't do experiment in 4 and 5 dimensions, but some people have done simulations, and we continue to work with this generalized Fibonacci number in this generalized divine proportion. So I did that in 98, and it sat around in the literature. And then in 15, one of my students, Heinzen, said, hey, let's try this with a computer simulation. And he led the way. And I'm going to call what I've done the restricted hierarchy model. It's very restricted. It's a hierarchy of 2, 4, 8, 16. And we're also going to do DLCA simulations. Here again, I've got a 2-dimensional and I've got a 3-dimensional spatial situation. I've got number of monomers per aggregate versus the radius of gyration. The blue dots are DLCA, which now, of course, in 2015 is what, a 40-year-old, 35-year-old process, been around forever. And we get a nice ensemble that's linear. The black lines are the hierarchical model, and they are sitting here at 16, 32, 64, and so on. And notice they're dead on with DLCA. Same thing in 3 dimensions. It's a perfect match. This simple model with all its restrictions duplicates DLCA on this graph. Let's look at the shape of these things. Let's remember the shape is a Fibonacci ratio, right? How do we define shape? Well, we fumbled around for a while, but then we came up with a way to take an aggregate and put the smallest circumscribing rectangle around it. We're going to have a length 1 and a length 2, at least in 2 dimensions. And we're then going to look at the ratio of L1 over L2. Here's what we get in 2 spatial dimensions. So the analytical result is the divine proportion. The simulations that we did of the restricted hierarchical model agree with that, with a small distribution in width. And here it comes, importantly. The classic DLCA simulations have a broad distribution, but it peaks at the divine proportion. Son of a gun, right? What about 3 dimensions? It works too. Now there's 3 ratios because you got 3 sides. You can ratio big to medium and medium to small. Then you can ratio big to small. So here's big to medium and medium to small. They're both broadly distributed. Here's the analytical calculation, green well with the analytical calculation. And here's the big to smallest, which would then be the square of this 3-dimensional divine proportion. And indeed, it agrees well too. So this restricted hierarchical model accurately predicts the fractal dimension, the prefactor, and the shapes of these aggregates. And of course, once you say Fibonacci and divine proportion, you go into all kinds of pseudoscience and things like that. I might add, you also go back to Martin Gardner and his wonderful mathematical games in Scientific American, which I grew up on in the 60s. So I wish he was alive now because I would love to hear his thoughts on this. But there's this classic work by D'Arcy Thompson on growth and form. He studies the biological side of nature. And to quote, "It shall widen and lengthen in the same unvarying proportions. And this simplest of laws is that which nature tends to follow. The shell grows in size, but does not change in shape. Our aggregates grow, but they do not change in shape, and their shape is given by the divine proportion and its generalization to n dimensions." That's what I claim. Here finally is the last word in my title. I finally get there. This is the sunflower, and it's the inflorescence is the nature in which the petals and the seeds come together in a flower in general. The sunflower has, meant to fix this, F11 and F10, Fibonacci number 11 and 10. Oh no, this is 9 and 10, I'm sorry. Regardless, there are 2 Fibonacci numbers in there, whether you look clockwise or counterclockwise. And this is a phenomenon that's seen throughout nature and other things, pine cones and other flowers and things. So, is there a connection? Don't know, but they're both non-equilibrium phenomena. You might recall the golden rectangle. If you take this side of length 1 and fold it down, you'll end up with another rectangle with the same proportions, which is sort of indicated here, and that goes on infinitum. We have invented the golden brick. Instead of a side, we take a wall, like a door, and we fold it over, and the brick stays in the same proportions of 1 to 146 to 146 squared ad infinitum, the golden brick. Soot and sunflowers. Is there a connection? I don't know. But with that, Gong, which is Vietnamese for thank you all very much. Any questions?
Let's unmute ourselves and give a round of applause. This is fantastic. Thank you so much.
I see a question. Or Stimuk. Go right ahead. Unmute yourself.
I don't see.
You're still muted.
Yeah, Forrest, you are muted.
Okay.
Yes.
Very nice talk. Thank you.
Thank
my
you.
question is, if you take an X-ray diffraction pattern, what kind of structure does it have?
Very similar to our optical scattering, because the extensive non-dense nature of the aggregate, even though the refractive index of soot is rather nasty and large, because they're ramified, there's a lot of air in there too, or space. And so that actually puts you into the diffraction limit. So the X-ray diffraction would yield the same thing as the optical diffraction. It would, of course, be at different wavelengths or length scales, because your wavelength is about 1,000 times smaller.
I see. Thank you.
Yeah, so people do small angle X-ray scattering that can somewhat overlap with our optical scattering, and they corroborate each other.
When you start forming your samples, let's say you toss one atom at a time, don't you have magic numbers coming in somewhere?
That's an interesting question. That's aligned with making nanoparticles of gold, for instance,
Right,
and so on.
right.
Yeah, we're an order of magnitude bigger. Our entities are not atoms. They're the little round monomers of, well, there they are, symbolically. Yeah, here we go. See these guys here? That is, I don't have a scale bar here, unfortunately, but it's probably on the order of 20 nanometers. So that ball of carbon is 20 nanometers. So we're already well beyond the 2/10 nanometer of a carbon atom.
Good point. Thank you.
You're welcome.
Hi, I was wondering, can you do mechanical experiments on your aggregates, and can you deform them and look at their mechanical response? Have you ever tried it?
Yeah, that was actually a leader in our aerosol field, Sheldon Friedlander, who passed away 10 to 15 years ago, was doing experiments with electron microscopy, and he turned up the power, or his student turned up the power too much, but he was looking at a fractal aggregate, and the carbon or form var surface of the electron microscope grid broke and stretched the aggregate, and then it broke loose and sprung back. And he actually started experiments then with an AFM and would try tugging and pulling on it. He was proposing that one reason why carbon black is useful in strengthening rubber. You might know that every tire out on the road is about 25% carbon black, and it takes us to 50,000 mile lifetimes and things. He was thinking that perhaps the mixture of the polymer of the rubber and the extensive and hence tensile nature of the fractal aggregates were supporting each other to make these things stronger. And unfortunately, that point of view died with Sheldon Friedlander. So I've heard nothing of that since.
Thank you.
You're welcome.
I was going to connect this problem to the problem of pollution in many cities around the world, right?
Yeah.
And basically ask you about the role of moisture and how that affects the
Role of
aggregation
what?
process. Moisture, humidity.
Oh, well, first of all, I'll say that another major area of my research is light scattering from particulate matter. And so the first paragraph of all my grant requests points out that we've got this horrible pollution over our cities and things like that. And somebody needs to understand how non-spherical particles like fractal aggregates scatter light. So I know about that. Of course, then I quickly leave that behind and go to my interesting physics. But moisture is important with these fractal aggregates, because if moisture condenses on them, the surface tension, as then the moisture then dries again, can change the fractal nature. And they call that cloud processed soot. And it tends to be smaller in size, but denser, and even loses its fractal scaling. And that's where the question about diffraction then comes in. Then my ability to use diffraction equations to explain my light scattering don't work anymore. Now I really do have a refractive index of soot, which is typically on the order of about 1.6 real part and about 6 to 8/10 imaginary part. And you can see that's nasty stuff, right? That's very refractive and very absorptive. So, and right now we are in my laboratory making soot generators that we're then going to pass and humidify them, dry them out, run them through our apparatus, and study how the light scattering changes.
I mean, it's a massive problem. So if there is a nice way of getting rid of the soot, that's good, right?
Well, Surjit, if you get rid of the soot, I won't be able to write these graphics anymore.
I know, that's why I was tempted to ask you this question.
Maybe that will cause my retirement.
Yeah. Any further questions?
Let me give you a question. Here's this golden rectangle. And again, you can kind of get into pseudoscience or numerology and things and find the golden rectangle all over the place. But I still can't help but ask the question of you. What's the most random rectangle? And by that I mean I can only describe random with an example. If I asked you to draw a rectangle, you wouldn't draw a square, would you? That's not a rectangle. It's got great symmetry. All the sides are equal. And I'll bet you wouldn't draw a rectangle that's 10 times longer than it is wide. Right? That's not very random. I'll bet you draw something about that proportions right there. You see where I'm going on this? If you throw 1,000 coins in the air, what are you going to get? 500 and 500. Well, 470 and 530. You know, you're going to get the Gaussian distribution, right? There's some sort of central limit theory to that. Is there a central limit theory to the most common rectangle? I don't know the answer.
I mean, it's a geometrical shape, but we also like the geometrical shape, or we think it's something that is normal. That's what we define it as. So there is a sense of perception here, and thereby our brain interpreting what is normal, what is average, what is typical. And I wonder if that plays a role.
That's a real good point.
So an alien may not like it, or well, may like it, but I wish we could check.
Well, that's a good point, because if you look at our fingers, 5 and 5, part of the Fibonacci series. So as what Surajit said, that's part of us.
Yeah. Yeah, Forrest touched upon something similar, right, during your lecture about the issue of how we perceive, and there is big time biology in there, and an averaging process, because, you know, our perception is not a singular process. It's a highly averaged time, average process in space, time, and everything else that goes on.
And there are quasicrystals related to that.
There we go. That's right. So it is a very, so I don't know, this is almost like this anthropic principle type stuff I'm thinking about, but.
Well, yeah, that's my point. If you go to 1,000 people draw a rectangle, and then you make a distribution of the length to width that everybody drew, would it peak at 1.6?
That takes us to a fantastic experiment that one can try with little kids. Have them draw rectangles of the sizes they like, and let's figure out if you get this golden rectangle is the average.
Yeah.
Right? So you can run an in-class experiment with little kids. I mean, these can be, you know, third graders, and teach them about the magic of numbers. Probably mathematicians have set up some experiments like that. I don't know, but they have done a lot of innovation in math teaching lately.
But people have done experiments with sheets of paper, and that size is kind of the preferred one. We never have paper for writing as a square.
No. So 8.5 by 11, is that about the same?
It's close.
Yeah, it's close. That's right.
Our credit cards, our driver's licenses.
That's right.
Can I comment on this question?
Yeah, please, go ahead, Ibrahim.
So I think the problem, I think you have to like accurately define like how to define a rectangle, because probably if you do a simulation of generating random rectangles, it is probable that the average shape would not follow the same golden ratio that you're proposing. So I think it's rather because our perception of rectangle is kind of shifted to the golden ratio, if that makes sense.
Well, I think that's what Surajit was saying too, that it just might be a human thing. And you can, the nice thing about the Gaussian distribution is, again, you can throw 1,000 coins in the air. It doesn't matter what our perception is. But here it seems as though human perception gets convoluted into it.
And we are very special. I mean, each of us, you know, we think whatever we perceive is whatever the world is, but that's not really necessarily guaranteed at all. Whatever we perceive is what we perceive with whatever sensory organs we have that are functional, right? So that plays a big role. Now there is some universality that one can expect to be there, but anyway, this is an interesting discussion. Actually, I would love for this discussion to be a topic of discussion soon in one of the talks, if somebody wants to discuss this. This is the second talk that has touched upon it. I think Oris was, and then, okay, Sriram is leaving. If there are no further questions, we'll wrap up. Yeah, yeah, go ahead. Your audio is cutting off. Maybe just. It's not coming through well. You might want to change your volume settings.
I'm at 100%.
Yeah, now it's good. Better.
Okay, good. Thank you. Yeah, so I just wanted to say that, you know, when we were talking about human perception and symmetry, we do see geometric symmetry in nature otherwise as well. For instance, in self-organization in biological systems, or even like avian flocks and so on. So therefore, you know, so there's a question of whether it's really exclusively related to human perception per se. Because we do see it in dynamics, you know, self-organization in fish schools and avian flocks and so on.
I think this is what Chris said. There are two kinds of things going on. One is that there is a general mathematical averaging, and one may be an averaging with regard to our sensory, systems that influence how we perceive it. So one may be more more of a plain average, but one may be a more specialized average, if that makes sense.
Okay.
Right, Chris? That's what you kind of.
Yeah. I confess it's always been hard for me to go to make this, you might say, an impersonal question about what the most average rectangle is. And again, I make the comparison to throwing coins in the air. That's impersonal. It doesn't matter whether I'm throwing the coins or an orangutan is. I have a feeling it's going to make a difference whether an orangutan draws the rectangle or whether a human does. One thought that came up in my mind right now is that I remember learning from anthropology that the way different cultures describe colors, the spectrum, varies with culture. I wonder if we found different cultures, if they would draw different rectangles, if the average rectangle proportions would be different. Again, with different cultures, especially if we could find some isolated cultures that haven't been in tune with the internet and et cetera these days.
Fascinating problem. I'm just fascinated by it from the standpoint of communicating with people, especially communicating with children. I find them the most creative little folks around. Yeah.
I mean, right. So these are my post-talk slides, but people see the divine proportion all over the place.
Yeah.
I guess that might be all I have. Yeah, that's all I have. And that's why some people are cautious with these sorts of things. So if you Google divine proportion, you'll get pictures of the Mona Lisa and how, Leonardo must have on purpose or subconsciously put all the divine proportions in there. Another thing I've seen is that your knuckle distances increase with the divine proportion as you wrap around. I've seen pictures of teeth. And I guess your belly button to your feet is 1.616 divided by your height to your top of your head to your feet and something like that. Of course, when I see things like that, as an experimental scientist, I say, well, let's just measure 1,000 people, see what it looks like, right? Mathematicians, I have a mathematics professor who poo-poos all those things because I think she wants 5 significant figures accuracy. But as an experimentalist, I don't measure the speed of light in my laboratory. I don't measure Planck's constant. I'm real happy with 3 significant figures of accuracy with all the work I do. And if we took 1,000 people and measured their belly button height and their head height and got 1.61 plus or minus 0.5, I'd be pretty damn impressed. That would do it for me.
Yeah, I mean, engineers are often happy with 10% error.
Yeah.
By the way, you have the same thing in music. The major sixth is a preferred interval. It's 5/3.
That's pretty close.
So now you can match your music with your DLA presentation.
Yeah, well, I could sing. No, you don't want me to sing. The next time I come to Buffalo, you can get a couple beers in me. Then I'll start singing for you.
See, there you go. We'll have a beer party before the talk, and then we can make it go. We should have had a virtual beer party today, excepting the timing's imperfect for that. Thank you so much, Chris. This was fantastic.
Well, again, I'm really, really pleased to have had the opportunity and honored to do it. So thank you all for your attention, truly.
Thank you. And if there are no further questions, we'll close now.
Okay.
All right. Take care. Bye-bye.
Bye.
Bye. Thanks, Chris.